Thank you. So I'd like to start by thanking the organizers, David, Satya, Harold, Christoph, and Gregory, who is not there. And I guess since this is the first talk, I can speak for everybody saying that it's great to be here after 2 years. I guess this is supposed to be in 2020. And also, I think it's great to talk to some real people. I mean, like for last 2 years, I think we have been doing things virtually. We keep meeting some of you virtually, but I mean, seeing in front of you, it's not this, I mean, it's something different. Yeah. So today I'm going to talk about this direction reversing active Brownian particle. This is done with my student Ayan Sandra, who is not here, and my colleague Urna, who is here. So if you have any hard questions, I guess Urna can answer it. Yeah. So this is based on this 4 publications, but okay, I'll be mostly focusing on this first 3, and then the third, last one, I'll just maybe just briefly mention. And so also, since it's the first talk and I have the whole week, so I have decided that, I mean, I'll not go into the very much detail, but like I give an overview of the things we have been doing, I think, these pandemic years. And so if you have more detailed thing, I'll be happy to have a detailed discussion. Okay, so let me start with something very basic, and which is basically we all know. So if you take a colloidal particle, so which is about a micron size particle, like in the lab, for example, if you have a polyester beads or something. So this particle, if you put it in water, so they usually have this motion, they have this jittery motion. And so if you take this particle in, let's say, so if you observe this particle at a time step which is larger than this relaxation time. So this relaxation time is basically set by the mass of the particle and then the viscous coefficient. So for this colloidal particle, this relaxation time is about between 10 to 100 nanoseconds. And so if you observe it at a time which is greater than that, so this is basically, you can describe the system by this Overdahl-Lanzwa equation, which is given here. Yeah? So the displacement in a given time, which is, yeah. So if you look at the displacement in a given time, so that goes like square root of the observation time, okay? And this noise is just a white noise, which you can think of as like a drawing from some Gaussian distribution. So so given time scale, so if this size of the particle is of 1 micron, so usually if you look at in 1 second, the typical displacement is about 1 micron, this thing. And if you look at in 1 microsecond, it's about 1 nanometer. Okay. So this simplest stochastic process, this is perhaps the simplest stochastic process, which is known as the Brownian motion. And as we all know that it has diverse application across all fields, right? And in fact, you can see the popularity of this motion, this thing, by just this thing here. Okay. So now if you look at a bacteria, so bacteria is more or less, like if you look at the size of the bacteria, it's more or less same of a colloidal particle. So these are rod-shaped objects. So it's about 1 micron diameter, and then length is about 1 to 2 micron. Okay. So if these bacteria, these are dead bacteria, right? So the kind of motion these bacteria will perform, it's similar to what we saw in a Brownian particle, but these bacteria are not dead. So if they actually perform a strikingly different motion, so what they do, so in a small time delta t, so they have an orientation, so it's basically along the body axis, and they more or less move in a straight line, and this is basically they have a ballistic motion, so the displacement goes like the time now, not the square root of time. And this orientation vector, so it has a stochastic motion. So the kind of stochastic motion, for example, the orientation vector can have, that depends on the particular model you looked at. And this kind of motion, which is the persistent motion along a particular direction, so these are called this active motion, basically. So for example, if you take a typical E. coli, so they moves with a typical speed of, let's say, 30 micron per second. Okay. So there are, if you look at a minimalistic model for this kind of active motion, there are two basic models, okay, more than two, but let me just focus on two. And these are known as a run and tumble particle and the active Brownian particle. For short time. So basically what bacteria do, this E. coli, for example, they move about, let's say, 10 to 15 microns before they basically changes the direction substantially. Yeah. So these are just the short speed. So this basically speed, which is, you can think of it like the, this V0 here, for example. So now, so there are two basic models. So one is that orientation vector. What it does is that it, decides a time which is drawn from some exponential distribution. And then at the end of this time, it just chooses a new orientation which is completely independent of the previous orientation, and it just chosen from 0 to 2 pi uniformly. Okay, so the model will be like in a given time delta t with a gamma delta t, probability gamma delta t, it chooses a new orientation. And with the remaining probability 1 minus gamma delta t, it basically moves with that speed or velocity in this case, basically, because you have this orientation distribution. So on the other hand, there are another model. So here the orientation undergoes a discrete jump. And in this other model, the orientation basically undergoes a continuous change. And what it does is that, okay, in a small interval delta t, so you have dx dt equal to v0 cos theta delta t, v0 sin theta delta t. This is the same as this one. But this orientation vector undergoes a Brownian motion in on a circle. So it's a Brownian motion in a circle. So in a small time delta t, this delta theta goes like square root of delta t, and this dr is the rotational diffusion coefficient, and this noise is drawn from a Gaussian distribution, for example. So these two basic, very simple model, I mean, they seem to successfully describe the dynamics of bacteria like E. coli, and also some artificial microswimmers like this xanthus particle, for example. So this is some recording of these trajectories actually for quite some time back. And you see that if you look at a wild type bacteria, it's more or less like a straight line. Okay, there are some deviations. And then it suddenly changes the orientation. And then again, it goes for a certain time, and then it changes the deviation. And this is, again, if you take an E. coli and then you can change some genetic codes, so you basically changes the way this flagella rotates. And then in this case, what you see is that this orientation actually changes continuously. And this is like the kind of active Brownian motion I was talking about. Okay? Yeah. But so there are just, so these two are, I was talking about bacteria, but there are certain kind of microorganisms, they actually do a drastically different kind of motion. So for example, if you look at this Myxococcus xanthus, so what you see is that, so these are, of course, they move actually quite slowly compared to the E. coli, but these movies are basically, so it just speed it up after making a movie. So they more or less does a active Brownian motion kind of thing, but then suddenly they changes the orientation completely. So for example, this one is this Pseudomonas putida. So you see that they almost moving like a active Brownian particle, and then suddenly they decide that they want to go back. They completely reverse the orientation. And again, they does a active Brownian particle kind of thing. So these are two examples, and then there are another several examples of they do basically this kind of this direction reversing model. These ones, I don't know whether they can change the, time at which they will change the. Yeah, so this one I do not know whether you can do that or something, because, yeah, so this one I do not know whether you can control the time at which it changes the direction, actually, yeah. So there are also this, some artificial systems, actually. So if you look at this particle, so this is a titanium dioxide particle, and then half is coated with gold. And so if you shine one kind of light, so it moves in one direction, and if you shine another light, I think this is UV light and green light, it moves in other direction. And if you switch off this, both the lights, it basically performs a normal Brownian motion. So this is like a Brownian motion because the light is off. And then if you shine the light, it basically, so it says this is like a Brownian motion, and then it's going in one direction, and then it suddenly changes the direction because you have decided to change the light. So to model all this, so these are the particles. So you have this titanium dioxide, and one side is coated with this thing. Then you shine a light on the particle, and so if you shine this UV light, it moves in the backward motion, no, forward motion, and then if you shine this green light, it moves in the other direction, basically. Yeah. So this one, for example, you can choose whatever time at which you, it's a switch between the direction. So you have this Brownian motion, and then you switches the direction, basically, yeah. So back in the bacteria's case, it's kind of exponential. At least it has exponential tail, yeah. And this one, of course, you can choose whenever you can just put a exponential clock in your computer and connect to the experiment, and then it will decide. Or you can put a power law, so whatever you want, basically, you can do with this one. So now if you want to model this, if you want a minimal model for this kind of motion, so this is what we call a direction reversing active Brownian particle. So now you have another variable, which is this dichotomous noise, sigma, so which alternates between sigma and minus sigma, basically between plus minus 1 at a rate gamma. So your discrete time dynamics in the 2D dynamics will be that, so with probability gamma delta t, the sigma goes to minus sigma, and with rest of the probability 1 minus gamma delta t, it undergoes this rotational Brownian, this active Brownian motion. So of course, if you see that this is a long time trajectory, if you look at it in a very long time trajectory, it will look like a Brownian motion. But if you look at the short time trajectory, so you see that, okay, this guy goes like that, and so this is like a segment of an active Brownian motion, and then it suddenly decides to change the path, and then it goes, and then, yeah, okay. So like the basic questions, you can of course ask many different questions, but like we are interested in these two basic questions. For example, what is the probability distribution if you observe a particle, just a single particle with these dynamics? And also, what is the first space's time distribution, or in more particularly, suppose you start from some vector r0 along a orientation theta naught. So you can now define the first space's time along these two directions. So one is what is the first space's time to the x-axis, and what is the first space's time to the y-axis. And so these are the perpendicular and parallel, and xy course, with respect to this theta naught in this case. So let's call it perpendicular and parallel axis. So that defines these two these persistent exponents, alpha perpendicular and alpha parallel. And the question we want to ask is, what are these things?
Reversing, you mean it actually goes 180 degrees?
Yeah, 180 degrees, yes, yeah. So here you do not see it actually goes 180 degrees, but because of this step size we took, so it actually changes completely, and then this one was the Brownian. So this particle will basically go something like, so it will go something like that, and then it changes completely, and then it will go like that, and then changes completely, and it will go something like that. So there's a small change in theta, and then there's a 180 degrees change in theta. So what we found is that, of course, you see like this typical behaviors what you see it in other active particle. So, but in this case, in addition to these typical behaviors, because of this interplay between these two time scale, one is set by this gamma and then other is set by this dr, basically 1 by gamma and 1 by dr. So it, in certain regimes, it actually shows something very non-trivial behavior and which is absent in any of the other active particle models, basically. And so I'll be mostly focusing on this, the new behaviors what you see it here, and probably just mention the other behaviors just briefly. Okay, so if you take this particle, this is just showing in 2D. So if your gamma is greater than dr and this is gamma is less than dr, so if you take a bunch of them and these are non-interacting particles, this is basically shows how they evolve. Yeah, they are all starting from the origin and they are all initially, I think, orienting in one direction. So you see that this case, actually this is dr is large. So more or less, like after this thing, it almost becomes an isotropic at even in the intermediate time. But in this case, when gamma is large, it keeps this anisotropy for a very long time. So if you look at this, how this, so blue and red is like the, so that if you just think of it like a spin, sigma values. So the sigma, blue is 1 sigma and the red is 1 sigma. Okay. So if you just forget the blue and red, now you see that this is more or less isotropic. Sigma is the your dichotomous noise, which is basically sitting here. No, yeah, it reverses, but your theta is still there. Right, so this is the part you should think of it. So you can, okay, so like for example, so you can just suppose you think of sigma equal to 1 plus 1. So in this phase, your sigma equal to minus 1. Theta is still changing. Now here it becomes sigma equal to plus 1. And then sigma equal to plus 1 throughout this. And then sigma equal to minus 1. Sigma is the telegraphic noise, basically. It has. Yeah, but flip, so you have two variables, right? You agree. I mean, it's a stochastic process. You have a two variable, I mean, if you look at it in one dimension, there is a variable x, y, okay? Then there is a variable theta, and there is an extra variable, which is sigma. So if you start with, let's say, all particles are, so initial condition, you start with along a orientation theta 0 with all sigma equal to plus 1, let's say. Everything is blue. Yeah. So you start with everything blue, and you have, let's say, 10,000 particles. They don't talk to each other. And then you let them evolve. Their orientation will change slowly. And once in a while, they also flip the orientation. Whenever they flip the orientation, you change blue to red. Right? That's the red and blue, these are the sigma values. And then when you flip it, orientation still changes continuously. Yes, yeah, exactly. Yeah, yeah, yeah. Yeah. No, no, no. Yeah. No. So depends on what is the quantity you are looking at. For example, if you are interested only in the isotropic steady state distribution, you can forget about the color here. Just think of it like it's a black and white trajectory. So this is something isotropic, but here you see that this is not isotropic for a very long time. So here anisotropy persists for a very long time, and in the other case, it becomes isotropic. So these colors are just to see that how it is. So this basically all this red, you see that they become things. So they red are initially on the left side, right? Because they have changes the direction. No. So that's right. So that is a very short time. So this is an intermediate time. So short time, of course, anisotropy persists because they have not flipped anything. So after that, this is an intermediate time, basically. Yeah. So what I'm saying is that in this case, the anisotropy persists even in this intermediate time, and this is the reason, this intermediate time, which gives rise to a non-trivial behavior which you do not see it in other active particle models, basically. Yeah. Delta theta? Yeah, yeah. See, like what happened is that in a small time delta t, see, because the noise is Gaussian, right? The width of the noise goes like square root of delta t. So in a small time delta t, if you do not have the sigma, theta changing by 180 degree will be a very rare event. You will not see it. They're uncoupled, yes. But because here you have this sigma, you see that actually orientation can change by 180 degree, and that makes a huge difference, basically. So now, so now basically it gives, so now you have this time scale, this gamma inverse and D inverse, they set this time scale, and so you can have this 3 or 4 dynamical regimes. So this is this initial regime. So you see that as I was saying that even this other particle, it is anisotropic. So this is the short time regime where all active particles will show anisotropic behavior because they just move along the given initial orientation. And then this is the intermediate regime depending on whether gamma is greater than D or gamma is less than D. So you have these two intermediate regimes. And then this is the final regime. So this is some kind of a, you see these regimes in everywhere, like all active particle models. And so what we see is that, so this is a regime where you see something non-trivial, basically, when a gamma is greater than D and in this intermediate regime. So this is basically xy, and then I'm just plotting the p of xy, basically. Yes. Yeah, so that's what we'll do. Finally, we'll not look at this thing. So this is what you will look at. You'll see. So now here there's no color of sigma. So what you see is that this is the intermediate regime. What I was saying that in that other figure, it almost becomes isotropic. So this is the regime, you see that it almost becomes isotropic. But on the other hand, in the first picture, this is quite anisotropic, basically. And here, behavior along this direction and that direction is very different. Sorry? This one, I'll talk about it. So it has a delta function, not delta function, but it has a basically accumulation at the end. And then you have some kind of a plateau, basically. So distribution has an accumulation at the end, and then there is a plateau. Yeah. So because it's most of the particles are basically going in one direction, they accumulate this thing, and then there is a plateau. So this plateau is also something, okay, very distinct. Yeah, at the end it has to be isotropic, right? Because if these are different times. Basically, this is a very short time. This box is. This is a very long time. Okay, and this is the intermediate time. And in this intermediate time, you have two behaviors depending on whether gamma is less than dr or gamma is greater than dr, basically. So in this one, if gamma is greater than dr in this intermediate regime, so you have a distribution is anisotropic. So if you look at along the perpendicular direction or along the parallel direction, you have two different behaviors. And this is what something I'm going to talk about, basically. So short time is, okay, let me just quickly tell about the short time behavior. Okay, short time is something, okay, easy because, okay, so this is your x and y. This is just the integration of this noise where this theta does this active Brownian motion. And then theta is basically, okay, it's an initial orientation. And then this one is basically just a Brownian motion, right? And we choose the initial condition, which is x0, y0 equal to 0. And then your all sigma is basically equal to 1. So now if you look at the time scale, which is much shorter than this dr inverse, right? So your phi, this integral of this noise, it doesn't change drastically. And therefore, you can basically do this approximation, and then you can see that this x and y, so this is basically a Gaussian process for a given realization of sigma. So if I give you that sigma flips at these times, so this is a Gaussian process, and you can write down the p of xy, xt, for example, completely. Okay, never mind the expression, but okay, this is, you cannot do this write down in an explicit form, but you can at least, evaluate it time by time numerically, and so this is what you look at it. For example, if you look at the x component of the direction, so what you see is that, okay, there is this peak you are talking about at the boundary, and then you have a plateau. And so this short time is actually, you can explain quite this thing, because this peak is basically like your ABP kind of motion, like active Brownian particle. And this plateau is coming from this directional reversal, basically. And in fact, you can actually take a 1D model, and if you take a 1D RTP with along this theta direction, even if you do a small calculation, it will actually get this plateau. And then if you go to higher order, you can even get this one. Okay. And you can similarly compute the first spaces one, and again, you have these two directions. One is the parallel direction, and one is the perpendicular direction of this initial orientation. And what happens is that along the parallel direction, it's like an 1D RTP, because theta, phi is changing very little. And you know that short time behavior is basically this alpha parallel is 0. So this is this one initially. Okay. But on the other hand, along the perpendicular direction, it's like a random acceleration process. And in this case, basically, you have a persistent exponent, which is 1/4. So this is what something saying. Yes. Another distribution mean if you take a uniformly this thing. Yeah. No, it will not hold. Yeah. Late times, it will not hold. Yes. So what will happen is that basically you will average. You can take this thing and basically rotate it with respect to that initial condition. If you have a distribution for a fixed initial condition, you can always average over. If you want to take a uniform initial condition, you just take this one and just rotate it in the space, basically, right? So then you'll see that instead of one single peak, you will have a boundary peak, but you will still have a plateau. So that one you can trivially calculate knowing this problem, basically. So intermediate regimes. So this is the actually most interesting regime, which you get something which you don't get it in this other. So in this case, again, if you look at the theta, so theta is your theta naught plus this Brownian motion, this thing. And in this case, so these equations are basically same as the equation what you have before, but now your gamma is very large in this regime. So what is happening is that this your sigma dynamics, so theta is changing very slowly, but sigma dynamics is very fast. So sigma dynamics essentially becomes a white noise. So if you write down this equation for delta x delta t, so if you look at this blue thing, it is a Brownian motion. But now if you look at the diffusion coefficient, so this is another stochastic variable. So you have a Brownian motion with a diffusion coefficient, which is another stochastic process. And in this case, so let me not go into the details. So you can actually, because your phi is again a quadratic variable, so you can actually take the average with respect to initially, with respect to this noise, xi, and then with respect to this phi, and finally what you have is basically you can find out the full characteristic function. And so this is true for any orientation, but now I want to look at the parallel and the perpendicular component. So these components are with respect to the initial orientation. So you see that the parallel component is basically is given by Gaussian, okay? But this perpendicular component is something quite different, and this is basically the distribution of the perpendicular component. So it has this scaling form. So it has this ballistic scaling. So this is this direction. perpendicular. So it has this ballistic scaling as opposed to the diffusive scaling. And this scaling function can be found exactly, which is basically this product of these two gamma functions. And it has this exponential tail, it is strange p factor pi. Okay, so this is basically this function for the perpendicular component, and of course, if you look at the parallel component, it's just a Gaussian basically. So this is the regime, this non-trivial regime, which is basically coming out because of this interplay of this Brownian motion of this theta variable and the telegraphic noise sigma basically. So this is a new regime basically what we have found in this case. So you can also look at the first spaces time for this problem. So again, the parallel component is trivial. It's like a Gaussian, so that the first spaces component is basically half, but we're just looking at the perpendicular component. And okay, so this is the Fokker-Planck equation. It's also true for the distribution, but okay, here is just the, because you are looking at the now survival probability, that the boundary condition is slightly different. And so I'll not go into the detail, like we can discuss it later. So if you basically solve this, so what you find is that the survival probability has this scaling form, and the scaling function, you can find it exactly, which is just the integral of the, or this f. So this f is where it's just given by this one. Justify, I don't, yeah, it's actually, yes, physically you say, right? I mean, no, hand wave, I mean, yeah, if I'm allowed to point to a mathematical formula in wave hand, I can do it here, because you see that this k and t, basically this is kt, right, instead of k square t. That already you see this ballistic scaling basically. Once you have the ballistic scaling, it's okay. Some function, why is it exponential or something, it doesn't matter basically, right? Yeah. 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 But intuitively why it happens is difficult to, yeah. Okay. So now, okay, so in this case, basically you see that now the survival probability now at large time is basically like when the argument is very small, and in this, when argument is very small, it's basically that expanding this integral for small z, and this is basically goes like z naught, and which is basically 1 over t. So is your persistent exponent for the perpendicular direction is 1, which is something new. And you can, in fact, you can also find out the first spaces time probability exactly, which is given by this one, actually, in terms of the same function f of z. And so here you see that, okay, this is your one for, this is the initial regime, but this is the intermediate regime. And here I have suppressed the initial regime because you can choose some parameter where this initial regime shrinks. So you see that it starts with 1 by t basically, and then this is the final regime. Okay. And these are the same plots, but with a scale thing, and then you can compare with the scaling function basically. Yeah, I'll come to that Brownian motion. So it happens to the Brownian motion where your diffusion coefficient is another stochastic variable. Because if you have a Brownian motion, if you reverse the direction, nothing will happen, right? Eta goes to minus eta is same as, you can take all trajectories of eta and then in between just reverse eta to minus eta. It's the same probability. So in that case, Brownian motion only changing the, because the direction doesn't have any meaning, right? Yeah. So it is not the regime where this problem is equivalent to the Brownian motion. Yeah. So that is the final regime where you see this half, there's a very late time regime where this problem is equivalent to Brownian motion, or basically any problems, if you look at a time scale which is much larger than the, whatever the correlation time, that will be like a Brownian. So that's like a very late time regime. Yeah. Depends on now whether you want to dominate it thermal noise dominates or the other noise dominates, right? See, because if you add a thermal noise, these are just independent processes. So if you look at the characteristic function, this is just a product of two characteristic functions, right? So you'll have this exponential of kt term, and then there'll be exponential of k squared t term, right? So now you have to, even there you have this two scaling function when you invert it. Convolution will have two scaling function basically. Yeah. And so this is the long time regime, your Brownian motion regime, and you see that at this long time regime, everything is isotropic, basically, right? And there's this, as you expect that, okay, it should happen because basically you have these noises, and if you look at a time scale which is larger than your internal relaxation times, then you can sample this path at a delta t, which is larger than this relaxation time. So you can argue with the central limit theorem saying that everything is Gaussian. And this regime is basically true for any random processes which has a exponentially decaying correlation. If there's a characteristic this thing. So therefore, there's nothing new we have been saying at that final regime here, which is true for any random processes. This is just, I just want to show. But what is new is that actually we could go beyond this hand-waving argument, right? This between this beyond this heuristic, and so what we could show is that in this paper that so if you take a so basically your active particle is given by r dot equal to v, right? V is the self-propulsion velocity. So v can include whatever the model of v you choose. So this P of xvt will have some kind of Fokker-Planck equation. So where this is like this advective term, and then you have something like this. And this LV, this operator will be model specific. For example, if you look at this graph where this V is V not sigma cos theta, so this operator will be something like this is how the theta changes, and this is how the sigma changes, for example. So if you look at RTP, so it will have a different dynamics. It will have a different form. If you look at ABP, so for example, this term will not be there. Right? So, but this form is very generic for any, almost all random processes basically where, so you have the dynamics of V which drives your this X, and V has an independent dynamics basically. Okay. And now, so what we have found that there's you could actually find a universal framework. So where if the V dynamics leads to a steady state, like for example, in this case, the theta dynamics and sigma dynamics, it has a steady state because theta goes between 0 to 2 pi, or sigma flips between plus and minus, so it has a steady state. So if it is a steady state, right, so it is basically can expand P of Vt in this eigenbasis, and then, so this is your steady state for V. So then you can treat this tau 0, so tau 0 is basically the relaxation time scale of this V dynamics, and T is your observation time, so this you can treat as a small parameter, and then what you can show is that this rho of xt, which is basically the distribution of x component where you integrate the V, so you can, it has this form. So basically it's like, you can expand in tau 0 by t where this t to the minus k is just absorbed in a0 of 2k. And the lowest order, it satisfies the diffusion equation. So this lowest order basically gives you this Gaussian form, which we got it earlier by heuristic, central limit theorem. So here actually you can get it exactly starting from your Fokker-Planck equation. And in fact, you can go beyond that and you can go to any order. And what we could show is that basically at any order, this A02K, so it satisfies a inhomogeneous diffusion equation where your source term, so that of course the functional form is model specific, but the source term only depends on the solution of this A0 to N of the previous orders basically. So you can recursively basically go and solve this. So, And then, so you have the solution. Of course, zeroth order is this Gaussian, right? That's what your heuristic central limit theorem will tell you here. But you can, in fact, go beyond Gaussian. And in fact, you can see that you can write down the, like, for example, this A02K for any K, so it has this scaling form. So it says it's diffusive scaling. And this Q2K, it is basically given exactly by this, where this source term is basically the scale source term, whatever it is, S2K. And this U and V, these are just this is the harmonic polynomial, and this is this function, which are basically the solution of this harmonic diffusion equation. Okay. But so this is initially, okay, we thought it was a bit strange that this, but now we understand this C2K. This C2K is still an arbitrary constant you have to determine, right? And that C2K you cannot determine, for example, from any symmetries of this A2K or just normalize of this thing. So this you have to determine independently from the moments. So you have to also compute the moments at the kth order. And from the moments you determine this A2K. So these moments, again, you can determine recursively starting with your original Fokker-Planck equation, basically. Okay. So that basically gives you the full this thing. And for example, in this case, you see that, so this is the initial Gaussian. This is what I showed you earlier, like this from the central limit argument. And now, so this is the corrections, and you see that this is Q2, this is a Q4, and this is sort of Q6. So this, you can, so these are polynomial. For example, Q2 is a Z-4 polynomial, and Q6 will be a Z-12 polynomial, but these polynomials you can actually find exactly, basically. Okay. So, okay, so this is, again, this persistent exponent, basically, okay, so this is the perpendicular component. So this is 1/4 was the one which is given by this random acceleration problem, that's the initial time. This is what this intermediate regime, this is the non-trivial regime what we have found. And these are basically the Gaussian regimes, where you have this persistent exponents, which is half. Okay, so now you can take the same problem and put it in a potential, harmonic potential. And now you want to know what is the steady state, for example. So again, you can, okay, so this is the potential, and so you can write down the Fokker-Planck equation directly, which is a potential. And then we are interested in the steady state where this is equal to 0. Okay? And so we are basically interested in P of xy. We don't want the color of this particle, so you just sum over its final colors, sigma. And so again, you have this now 3 kind of this thing. So one is your trapping strength, mu. Then other is your direction reversal. And the third is the diffusion, rotational diffusion. You have these 3 parameters. And these together, basically, they give rise to various steady state. And so this is a schematic, this thing. So these 2 steady states are basically, you see what your other typical active particle cases. Basically, you have a passive case where everything is accumulated around the center. So this is like a Boltzmann distribution here. And this is the active one phase where things are accumulated at the boundary. So these are like typical passive and active phases. You see it, for example, in the RTP, or you look at in the active Brownian particle. But here we have 2 other phases where, so you have a passive phase where again things are accumulated at this thing, but the central part, it has a logarithmic divergence now. If you look at the x, P of x, for example, or basically there is a divergence at the center, and even in the active phase, so you have accumulation at the boundary, but again there is a central divergence, basically. Oh, no, these colors are just, I think, just a mathematical shows that this is basically going from larger to smaller. This is just the way, I don't know, mathematical plots, but there is no color code. Yeah, it's basically, yeah, so it just says that this is basically going down like that, yeah. Because I think if you just put one color, it will be difficult to see. I think that's what, that's what they, So basically this, again here, we have these two novel phases which you don't see it in this other other cases. And so before going to the details, so actually it's useful to look at the trajectories in these different cases. And if you look at this passive one case, you see that basically this is a kind of particle motion. It's mostly concentrated along the near the origin, so which basically gives rise to your Boltzmann distribution. On the other hand, active one, basically it's accumulated in the boundary in between. Okay, there are some excursions. But on the other hand, what happens in the active one and passive one? So again, active one, it's basically concentrated along the or around the origin. But unlike this, you see that most of the trajectories are actually passing through the origin. And in this case, again, it's concentrating along the boundary, but then it goes back. So unlike this case, most of the trajectories are going through the origin. And this accumulation of trajectories which goes through the origin basically gives rise to these divergences at the center, basically. And in fact, you can analyze these things. Okay, this one, let me just, okay. So this one is just a passive one case. So let me not spend time here. So this is basically the, what you get is basically this Gaussian distribution for here because it's a harmonic potential. So this is the typical passive phase. You see it in any active models. There'll be some effective diffusion coefficient, okay? And then similarly, you have this active phase. So where active phase is basically active one phase, which is essentially similar to basically the active phase, what you see it in the active Brownian particle. Right? For example, earlier, Urna and Satya, etc., they looked at this model, and Abhishek, etc., also this looked at this model. And then, so this is basically your typical active phases. You see it in active Brownian particle. Okay. So basically in the active phase, so if you look at the position distribution, there is in the marginal position distribution, so there is an accumulation at the boundary. But so this is something new, basically what we find it here. And this is what I'm just going to spend a little bit of time. So it's basically, okay, so it's useful to just write down in the scale variable, right? So you have basically this gamma by mu, so this is your one parameter nu, and then this epsilon, which is this dr by mu. And this dr by mu is very small, basically. This epsilon is very small. So you have this epsilon and you have this nu. And now, so what is happening is that basically, so if epsilon is very small, so dr is very small, so what you can do is basically you can think that at the first approximation you can neglect this term. So then what is happening is that, so you are looking at a steady state, so it's basically a run and tumble particle along your orientation theta, okay? So you can just solve this thing with the fixed theta, and then you average over theta, right, to the lowest approximation. And so in this case, what you can do is basically you can disentangle this motion along the parallel and the perpendicular direction, so it's along a particular theta, and then this probability day becomes independent. This two motions becomes independent basically for a given theta. So it's basically this probability day factorizes, and so now the perpendicular direction is basically a run and tumble particle. So this with Satya, Abhishek, etc., we looked at some point. So and where this is given by this one. So this is for a given theta, but now theta of course changes. Theta changes very slowly, and so you can now average over the direction of theta, and when you average over the direction of theta, so you basically have this p of xy, which is given by this, and where this is your scaling function. And you see that there is a divergence at the center for both cases, active and passive. So active and passive basically determines by whether nu is greater than 1 or nu is less than 1. Right? So this divergence is basically present in both active and passive cases. And so you can also look at the marginal distribution, And in marginal distribution, basically, okay, so you average over the other variable. So this is your new scaling function G nu, and this is basically exactly given by this. Okay, so first you look at the tail, so which basically determines whether it's a tail around the potential, end of the potential basically, so which it determines whether it's a active or passive phase. And if there's an accumulation, it's an active phase, and if it goes down, there's a passive phase. And you see that basically this tail changes the behavior depending on nu. If nu equal to half, so there's a accumulation. Nu less than half, there's a accumulation there, but on the other hand, nu greater than half, there's no accumulation. Okay. So now, so that basically says that this transition from the active to passive, but you can look at now the central part, for example, in the passive part, and so the central diverging peak is basically given by this. So you can actually analyze this function, and you see that there's a log divergence at the center for both active and passive cases. And for passive cases, basically what you see that, okay, so if you can actually look at the, you can now, so this is the passive case, nu is very large and z going to 0 in this passive case. So if you look at the scaling functions, okay, so you say that this is exactly given by this, and you see that this tail in the passive case is still Boltzmann, W goes like from this thing. But if you look at the peak, so it's accompanied by a basically logarithmically diverging peak at the center. So this distinguishes these two active and passive phases from your regular active and passive phases, basically. Yeah, it will be always coming to the origin. The shape will be different now depending on which, I guess yeah, I think the active, the passive phase will be same.
Like in the Mexican hat, this would not happen, right?
Mexican hat, it will not happen. Yeah, because it will be depending on the width of the in between. It may not even come to the other side, right? Because then it's like a active particle in one of the potential. So that depends on what is the intermediate width, right? But if you assume that it can come, yeah. You always pass through origin. Basically, what is happening is that there are a lot of weight accumulated at the origin. So if you can somehow avoid going through the origin, then you will not have this log division. Yeah. So it's basically happening is that while it's basically all the things are going to the origin. Okay, so then we can actually come up with a qualitative phase diagram. So you have these 3 parameters, and inside, so you have this active phase inside, and then, okay, you have these passive phases. And so what we did is initially, basically, okay, we look at in these various limits, and we can find analytical answer. And then we did numerics and then see that, okay, this whatever answer we get analytically, so they qualitatively, they remain same actually when we come out of these regimes, basically. Yeah. So to summarize, I don't know how much time I have. Yeah, so I'm almost done. So to summarize, basically, so here we have provided a comprehensive analytical understanding of this direction reversing active particle, and then so this presence of this directional reversal, rotational diffusion. So it gives rise to some non-trivial regimes which are absent in other active particle models, and in the harmonic trap, again, because of this directional reversal and this rotational diffusion and trap stacks, so they lead to a complete complex phase diagram, and in particular, we basically there are we find these two phases which is not there in the typical active particle models, and okay, yeah. So this is what I said that basically. So there are two novel phases where basically there is a diverging central peak. Okay, so let me just mention this thing. So I was talking. I told that this at this intermediate regime, this motion is like a Brownian motion with a diffusion coefficient which is stochastically evolving, and we found that actually there are a couple of. So we basically came across this while studying this problem. And it seems that there is a considerable interest studying this stochastic diffusion, Brownian motion with stochastic diffusion coefficients. And it's basically, you can just think of it probably a model for, I don't know, if you have a for example, motion of a colloidal particle in water, and for example, you are heating the water or something like that. So on the average temperature is growing linearly, but there will be fluctuations, and that will be probably modeled by something like a Brownian motion with a stochastic diffusion coefficient. It also, I found that, okay, there's some problems in economics where this Brownian motion with stochastic diffusion coefficient appears. And so this is basically the model what is, so you have this dr dt equal to eta of noise, eta. So if the d is constant, this is your normal Brownian motion. But now d, so d you can just write is some omega square, and this omega square undergoes another independent Brownian motion. So where this noise zeta and this noise eta, they are completely independent. And so if you take this problem and then in any dimensions, in fact, if you look at so it's an isotropic problem because you start with at the origin, and so it's completely isotropic. So you can study this radial distribution, and you see that this radial distribution has this scaling form in any dimensions. And so in fact, in odd dimensions, you can find it explicitly. So it's basically given by this derivative of this function f of z, and where f of z is the same function we have found it there. So for example, in one dimension, so this distribution is basically the same what we have found. And in general, for any dimension, you have this exponential tail, basically. So what, yeah. And so you can now ask, okay, if you, so let me not give motivation now why we have studied this one, because, so we basically came across this problem while we were studying this, this active particle problem, so that we said that it maps to this, and then we studied this in higher dimension with and without resetting, and then if you actually study this problem with resetting, where both position and the diffusion coefficient, you basically reset to 0 at some constant rate alpha, and what you find is that, so you have a non-equilibrium state which is given by this scaling function, and this scaling function, so it has a stress exponential tail. As opposed to, like, for example, if you look at just a Brownian particle which reset to origin, which Satya and Martin Evans, they looked at it. So you basically have this exponential tail there. So you have a stress exponential tail. And in 1D, what you have is that you also have a logarithmic divergence at the origin, basically this problem. So this is basically, okay, similar to what we have found. And in fact, this, for any higher dimensions, what you see is that, okay, so you have this universal tail, but at the origin, they becomes a constant for higher dimension, but in one dimension, so you have this tail. I think, yeah, so I think, thank you for your attention, and I'll stop it here. So maybe I'll just put this as a summary. Yeah, thank you very much.